Hello everyone, we're ready to start. The topic today is we'll finish BGP and we'll do a few things about the application layer, and we will test all of this tomorrow as usual. Today we're talking of something subtle about BGP, which is very illustrative of how all this story of computer networking has been developed and deployed. The problem here is how does BGP interact with the routing table and with the interior routing protocol? If you would ask me how to do things, or if I use the differential encoding methods, i.e. I try to imagine what is my solution and I compare to what is really happening, here I will see many differences. The textbook solution, that's the one you read in many textbooks in BGP, but it's not really the one that is implemented without any modification, is redistribution of BGP into the I-GP. BGP is at a high layer. It's about autonomous systems talking to each other. And what happens inside an autonomous system is the business of the IGP, OSPF, for example. So the normal thing to do, which is done, but we will see with some caveats, is that the routes that are learned by BGP are passed to the IGP. This is called redistribution. And normally we should stop there. However, there is something else that is always done in the software. All the pieces of BGP software that I know, they always do what is called injection. Injection means BGP does as if it would be an interior gateway protocol, a routing protocol such as OSPF. It says, I know routes, how to go various places. I write this directly into the routing table of the router, into the forwarding table. I call it injection to make the difference here between the two. So remember, this is always done in practice, and this is done if you enable it. This is where we stopped last time. We saw also that some systems don't like to do redistribution, and in order for absence of redistribution to work, we need what is called recursive table lookup. This is where we stopped last time, where we saw that if a BGP router puts into the routing table, normally into the routing table, you put the next hop. But what the BGP router will do is it will put the BGP next hop, which is not the same thing as the next hop we expect to find in the routing table. The clean thing to do would be not to do it, but this is not how things are done. You fix this problem by adding a capability which we called recursive table lookup. We allow this to happen because of BGP. And that means that when you find a next hop into the routing table that is not on link, as expected, you have to go at least a second time into the routing table to find what to do. This is where we started last time, right? We saw that, for example, if R2 injects into the routing table next hop 222, a packet that comes from R4 to this external destination will first go to the routing table. We find next hop is 222. Remember, 222 is considered as an internal network by the ASX here. So there should be eventually, after doing a second table lookup, you should find where to go. And the answer here, you should go to the east interface of R1. Right? Now, we discussed at R2. What will happen at R1? For exactly this same packet. It's a packet that has been sent, is coming from R2 and is going to 18.1. something. Which way will it go at R1? The majority says B, but this is not correct. B means it's forwarded to R6, which is what we would like to happen. But in this network, R2 is not on link with R6. So the only thing that R2 can do is find the MAC address of R1 and find the interface on which R1 is, find the MAC address of R1 East, and send it to this MAC address. That's the only thing it can do. R2 knows that the next hop is 222. But when the packet, the packet will go from R2 to R1, that's fine. But R1, which is not a BGP router, doesn't have any information about this external route, right? So the correct answer here is C, it doesn't work. So if you simply do injection, which all BGP routers always do, if you do that alone, because you refuse to redistribute into the IGP, then you still have a problem. The problem is that the places in the middle, like this one, they don't know how to go to this one. Right? How would you fix that? Imagine you're a software engineer, not a scientist. Well, a simple solution, which is invariably the one that is done when we don't do a redistribution, is to run BGP everywhere, also in R1. The reasoning is those external routes, they're directly injected into the routing table. So in order for all routers to know, they need to know about all the external routes. How can you know about all the external routes? By running BGP. So we find this paradox that some networks run BGP in routers that are not at the boundary to any external network, just because of this reason, in order to be able to gain the information about all the external routes. So that means here you will do a mesh with those three routers. R1 would run, of course, only internal BGP, it doesn't have any external BGP peers, but it will get from R6 and from R2 all the external routes. So R1 will get the information of 18.1/16 with BGP next hop 2222. It will install it in its routing table, and then when a packet comes, by recursive table lookup, by looking up twice the routing table, the packet will know now it has to go to 222. Right. So this is what is done very often when you don't do redistribution of BGP into OSPF, and that explains why we have this paradoxical behavior where we run BGP in something that a priori doesn't have any reason to do it. Here. We still need OSPF or something in a network like this. Even though we distribute all the external routes with BGP, we still need to distribute the internal routes. We still need to know, how do I go to 2222, for example? So we still need an interior routing protocol. That's a method that is used in some networks. The interior routing protocol takes care of all the internal routes. BGP takes care of all the external routes. Right? There are alternatives that I will not discuss in detail. We'll talk more about MPLS in some other course. Another alternative could be to use source routing. Right? R2 knows how to go from R2 to this destination. So what R2 could do when a packet comes to destination 18.1 is to say, okay, I go to my routing table and I see a BGP next hop that is 222. So what I could do is use loose source routing, add a source routing header, which is add to this packet the information, now go to 2222. That is a clean way of separating the concerns. The information about external routes is handled only by BGP. The information and that includes the next hop, which are all internal. And how to go to the next hop? Well, we add the source routing information, which is the goal of source routing here. This may come in the future. That is not used in this way because source routing today is not very much deployed by ISPs because of security reasons, although with segment routing that may come in the future. And MPLS is essentially doing the same thing with different means. So that's a different way to do. So some big networks use MPLS to avoid that problem of distributing BGP. Now to the ugly thing that you will need to discuss for the lab. I've said that the thinking of the people who implemented the first implementation of BGP, and that was invariably copied, but there are N different implementations of BGP. One of them we use in the lab is Quagga, is a fork of Zebra, which itself was a fork of something else. All those implementations, they copy more or less what Cisco does. And what Cisco does is it implements into the routing table, it injects into the routing table all the information that all routing protocols have. So typically, we would have OSPF and BGP. Believe it or not, it's possible to have multiple routing protocols. You can have other routing protocols than OSPF, but we won't talk about that now, which can easily create conflicts. We'll see an example in a minute. So this conflict is handled by adding a weight, which is called the administrative distance, to a routing table entry that essentially is a priority field saying, depending on which protocol found this entry, here is a priority I should associate to it. And those are the default weights. E-BGP as the highest priority, I-BGP as the smallest, and OSPF as a higher priority than I-BGP and than RIP, although we don't expect to find both OSPF and RIP. I'll show an example here. Here, so I'm assuming, unlike what I discussed a minute ago, I'm assuming that we do the normal thing, I would say the expected thing. We redistribute into OSPF the BGP routes, because OSPF has a way to do that. Let's see a possible sequence of events. So R6 gets this external route, it injects it into its routing table, and redistributes it into OSPF. That means it says to OSPF, I am attached to this with some costs that you need to, by configuration, to decide. Here I'm assuming, for example, R6 says to OSPF, I am connected to that guy, and the cost for me is 20. Typically, you take a high value, much higher than all the values you would have inside your network, because it's an external route. You consider it further away than anything internal. But before that happens, it's quite possible that R2 has received from I-BGP the same routing information. Now, because by default, the behavior, not by default, in practice, the behavior is you write into the routing table what you know. R2 will write this in its routing table. It will say, I know how to go to this destination. I put this thing we discussed a minute ago called the administrative distance. It comes from I-BGP, so it's very high, which means low priority. And I put whatever I know. Here I put the next hop, which is not on link, but we expect to be able to do when you do that kind of injection to the recursive table lookup. Of course, we expect that OSPF will distribute things, and this will happen indeed later. Assume R6 puts into OSPF, as I said, redistribute into OSPF. OSPF will, with its topology database flooding mechanism, will pass the information eventually to R2. So R2 will have this map. R2 will know that R6 has an X hop 222 that leads to 18.1. Running Dijkstra to R6, R2 knows to this destination, we need to go towards R1. So R2 here, via OSPF, will add this information. Now, it will add the next hop, which is the next hop computed to OSPF. There's a typo in the slides. I think the slides that you have online don't have the correct line here. It will add a cost, which is the cost computed by OSPF, which is the cost of the injected by R6 plus the OSPF cost. I'm assuming here these links have a cost of 1 for OSPF. That gives 22. It also has the second route that is put by BGP. Now, this route doesn't have a cost because BGP doesn't have a cost to destination. And the rules of this router is you pick. So we see there is an injection conflict. We have to the same destination. We have two possible next hop. Now, it doesn't really matter in this specific case. It goes in the same direction. But you could easily imagine cases where IGP makes a decision which is not, BGP makes a decision which is not compatible with the best route chosen by OSPF. So you could truly have conflicts. In that case, the conflict is resolved by the administrative distance. We give priority to OSPF versus I-BGP. So I-BGP can be used to disseminate internally external routes, but we don't take this seriously if OSPF was able to do the same thing. But note here that, for example, if a route is injected directly by E-BGP, like this one here, it will always have priority because the E-BGP external administrative distance is larger. So if for whatever reason this router R2 picked as best route towards 18.1 another that goes this way, right? We would have here, through I-BGP, R6 would receive some information that may differ than the one it received from E-BGP. So, of course, one of the two will have to be winning. If the winning one is the E-BGP, is the I-BGP one, then there might be a conflict. I-BGP may say we go this way, and E-BGP might say we go the other way. Now let's see a number of other bells, what I call bells and whistles in BGP. They are easier to understand. We have seen the decision process that computes routes based on a number of set ordered list of rules. Of course, if you are now running a domain, you may want to have more freedom. So one of the rules is saying you look at the weight. So the weight is simply a way to say you should have a script that decides which weight based on your own criterion, and then BGP will pick in priority the routes that have a larger weight. Let me give an example here. Here I'm assuming I am focusing on AS4. It has two paths, one that goes for the rest of the world that go via AS2 and AS3. Perhaps it is paying a service to two different providers and doesn't want to use AS2 a lot, perhaps because the link is long and not very high bandwidth. So it prefers AS3. So one way to do this is to type in your script, that will write the route maps in all the BGP configuration scripts. It will say everything that is coming from AS3, I mark it with a preference of AS2 with a preference of 100. And everything that comes from AS2, I mark it with a preference of 50. So this you deploy in all your routers. It's only R2 that receives from E-BGP, so R2 will implement this. When R2 receives this route, this one here, from AS1, AS3, it will mark this preference. R1 will do the same. And this preference field is a field that is in principle propagated inside an autonomous system. That means, in particular, through I-BGP, R3 will receive whatever preference was marked here. So if we ignore the details of how the routes will be propagated inside this AS, which route will R3 announce to AS5? The majority said B, which is, of course, the intention here. So, in fact, R1 and R2 will both prefer this route. Even R1 will prefer it, because R1 will look at the weight first. It will receive from I-BGP the information from R2, so it will prefer it. So all routers in this domain will prefer the route that goes this way. That's the intention of this weight mechanism. Nobody answered D, but this would also be a valid behavior. An AS is never forced to propagate a route. We have seen, in fact, that, in principle, you want to propagate route, but not always. Peers, for example, typically don't propagate routes to peers because they don't want to, unless they're happy to serve as transit for somebody who doesn't pay for the transit. But in principle, you don't announce all routes to peers. So it's always legitimate to not announce. But if we announce something, it would be B. So that's, as you see, a very simple mechanism that allows you to manipulate the routes. Another one, let's skip the weight, is called the multi-exit discriminator, the MED, which was invented probably at another point in time because with the preference, high preference means it's preferable. For MED, its high number means it's less preferable. It's used in a different setting. Here I'm showing one of the examples we've seen already before, where one AS is advertising, is probably a customer of ASX, is advertising those two prefixes, 10.1 and 10.2. Of course, you probably don't advertise a private prefix, but for the simplicity here, I keep it. And R3 is announcing both 10.1, which is local, and 10.2, which is remote. But we indicate here a different multi-exit discrimination. That means multi-exit means Y has two exits to X and is indicating a preference. We would prefer to use this exit for this prefix and perhaps less for the other prefix. And R4 will do the opposite. So now it's a bit more subtle how you program your BGP routers. You need to program them to provide the multi-exit discriminator. We see that the MED is given between ASs. So it's given between different ASs. Now what happens between ASs? They are not the same companies. So you don't expect to give weights, for example, between ASs because you don't trust what other people are doing. It's not that you don't trust, you don't want to create mess by taking seriously the priorities that are indicated to you by someone else. So weights are not, and preferences are never propagated outside the domain because of good management policies. This is an exception. The multi-exit discrimination is propagated from one domain to the other, and it's typically taken seriously by this guy if this guy is a provider to this one. So if Y is a customer of X, probably then X will take it seriously because they have a business relationship. Let's test this on this little example. And of course, A, that's the intention. R1 will prefer that route. R1 is taken seriously, the MED, because, as we said, there's a business relationship between X and Y. So R1 will prefer this route for 10.1 and will prefer that route for 10.2, whatever the other criterion says. You could say, why do we do that if we have two routes? Well, one of the reasons for having this complicated set of criterions with priority sorting is the philosophy in the internet when at the peering level between different peers is to have a large redundancy because many things can fail. And if you connect to others, you may want to be robust against failure. So it may be that this link fails, it may be that R1 fails, or here that R3 fails. So in a case like this, if this router R3 fails, then what will happen is that the routing, the normal routing, which is now avoiding hot potato routing, we saw that by default we obtain hot potato routing. With MED, we can go against this behavior and concentrate the routing to where we want it. So we want, in this case, that the long distance links are used inside X because we pay to X to get the service. So perhaps we have long distance internal links here, but perhaps we want to keep them for the traffic, for backup, or for whatever purpose here. Now what will happen when this crashes? R1 will detect that this router is no longer valid, so all the routes it has obtained from R1 will be deleted. Now it has remembered in its adjacency rib in, it had remembered the route to 10.1 that had a bad MED that it did not select, but it still remembered. When the other one disappears, it gets the other one. So traffic to this destination will go this way, which is better than going nowhere. Hopefully there is a link inside Y here. So that allows to have backup. We saw an example of a route being lost. What happens when a route is lost? You guessed right. The purpose of the principle of BGP is we try to inform in principle only about changes. In particular, when something is lost, then we send a negative update. So we send an update message with a withdraw field. In principle, all the messages I've shown before are advertisement fields. The update contains a route, but an update can also contain a negative message, withdraw this route. So this is what will be done. And in principle, it is sent as soon as possible. Right. Now that leads us to another problem. Once you do that, imagine that you have, a router is a computer with dedicated hardware for processing packets fast, but it's a computer. And therefore, computers have all the problems that we know. They crash, processes can crash. Routers are very sophisticated computers, so in principle, they have systems for automatically rebooting when it crashes. So when if the BGP process crashes, it will generate lots of alarms everywhere, and in principle, it will reboot automatically. Now, what that can cause is that when a router crashes, if the crash is not very fast but takes 1 minute to reboot, for example, all the neighbors will detect that this router is dead. So they will do all the things we discussed a minute ago. The routes will be withdrawn, and the withdrawal will propagate. And then a minute later, we'll start having update with advertisement where we reinstall the routes. So we will propagate the routes again. In fact, that creates a denial of service attack against BGP, because now all BGP routers are very busy adding and removing the same routes again and again, and that may propagate to a large fraction of the internet. What would you do against that? Well, you need to put some friction in the system. So this friction is called route flap damping or dampening. The idea is that with every route in the adjacency rib-in, when you receive a route, you keep all the information that comes with the route, and then you add a counter and a state. The state says whether this route is valid or whether it should be suppressed. That's called the suppressed state. And a counter is shown on the y-axis here. The counter is something that is a penalty counter when it's initially 0. And when a route is removed, I'm showing here on the x-axis time, and W and U letters means events, point in time where we received a withdrawal or we updated the route again, means we received an update message with an advertisement, positive advertisement for this route. So here I'm showing exactly a route flapping episode where the route is removed, added again, removed, added again, etc. When the route is removed, the penalty is increased. And if the penalty is small, nothing happens. If the penalty is above the upper limit here, the route is suppressed. That means, for example, this is what happens at the third time the route is removed. The penalty increases beyond the suppressed limit, then the state of the route is kept in the adjacency rib-in. If I'm a BGP router and I receive this route, I remember this route has already existed before, so I did not delete it from my adjacency rib-in when I received the withdrawal. I kept it with the updated value of the counter. And now, if the value of the counter becomes very large, I put it in the suppress state, which means that whenever this route will come again, I will, depending when it comes, I may not use it. So we increase the counter. Of course, we need a mechanism to decrease it. And like in many artificial intelligence systems where we introduce some concept of forgetting or forgiving, this decays exponentially. So this route has hurt me, BGP router. I remember that it has hurt me, but I will decay the weight exponentially. So if you hurt me 20 years ago, perhaps I've forgotten. If you hurt me 5 seconds ago, I will not take your route seriously. So there is an exponential decay, which is computed whenever an event occurs. So in detail, when this first route with withdrawn, you don't delete it, you keep in the adjacency rib database with this penalty function. Whenever it's updated again, you compute what is the value on the curve, where are you on the curve, and you look whether you are where you are. Here the suppressed state was do not suppress, so we accept it, we reinstall the route. Then a few seconds later, it's deleted again. We add another penalty. Then nothing happens. We still accept the route. Here we withdraw it, so it decays at this this should be an exponential curve here. And the third time it happens, the penalty puts us above the suppressed limit. So we keep this route and we remember, don't use it. So this route does come back here at this time. When it comes back here, nothing happens because it is suppressed. So we see this route coming, but we ignore it. So we ignore some information we have. Then we see it withdrawn another time. And then the problem with the router that caused these oscillations is fixed. So it's updated only once. But here it is still not used until enough time has passed such that the penalty is below the reuse limit. And this time it will be typically tens of seconds. So during the interval 0, T1, we accept the flapping of the route. But this has happened too many times within a short interval of time. During T1, T2, we don't accept the route. So this is one of the additional mechanisms we need in BGP, which is called route flap damping. There are many systems that have that kind of problems, and they all use this similar system. Private AS numbers. Here's an example of use. Imagine this is EPFL, and it's connected to switch at several points. Then it may use things like multiple exit discriminator to do all the nice things we have described before. However, EPFL doesn't have an AS number and would still like to use BGP to talk to switch. If that's the case, you can use a private AS number. Just like there are private IP addresses, there are private AS numbers that are supposed not to be visible in the big internet. So here the example of use would be very simple. EPFL, when it uses BGP, uses its private AS number that it has agreed to with switch. And whenever switch gets this information and propagates the path further, then it will replace this AS number. It will either remove it or replace it by its own AS number. So that EPFL hides behind switch. That's one possible use of the private AS number. Another possible use is what is called confederations. One problem of BGP is the need to create the BGP mesh between all BGP routers inside a domain. You have a domain with 1,000 routers. Each of the BGP routers need to speak to the other 999 routers, right? Which may be okay or may be a bit much. Remember, there is an adjacency rib in for every BGP peer that you speak to, so that may be a bit too much. No problem, we know how to fix that. When things are too big, we create a hierarchy and levels. So one way to organize a big AS is to make it as if it would be multiple ASs. So you can, this is one big AS here. You can organize it internally as if it would be made of multiple external domains to which you give private AS numbers, and you can run BGP inside this domain. So to the rest of the world, of course, these private AS numbers will be translated on E-BGP between the truly external BGP between your domain and the rest of the world. You will not use those private AS numbers, you will use the number Z, but internally you have a protocol that is still called external BGP. So that is one trick or one pattern we can use to make the I-BGP mesh not too large. It's called a confederation. The good thing about the confederation, apart from the stretch of mental agility that you need to accept the fact that an E-BGP session is inside a domain here, apart from that, the benefit is that everything is the same as is business as usual. You don't have to learn a new protocol. Some people don't like it, so they've invented something else, which is essentially doing the same thing, but it's called route reflectors. So route reflectors is something added to the I-BGP protocol, so to BGP that is used internally, which allows some special routers to act as cluster heads. And instead of requiring that there's a full mesh, that all routers are meshed with everyone, every router should be meshed with one cluster head. And then the cluster head will pass the information to everyone. We won't see in detail how it works, but sometimes you will see those words, a route reflector. A route reflector is simply a cluster head inside a BGP mesh that is passing the information, avoiding that everybody speaks to everyone. So it's a mailbox system, if you want. Apart from that, it's BGP business as usual. In all the figures I've shown, I've shown BGP interconnections appearing at boundary between networks. So if you're Swisscom, you talk to Sunrise, you pull a line between Sunrise and Swisscom, and you put a BGP router at the end of every line. That's one way of interconnecting, but there's another way, which is using interconnection points. There's one in Switzerland called SwissX. There are famous interconnection points in the US, May East and May West. Those are big interconnection points. An interconnection point is simply a private company that rents the basement, and puts lots of racks with routers and big Ethernet switches, and allows whoever wants, whoever is an ISP in principle, to connect to them and to peer with other using BGP inside this interconnection point. So it's not very expensive. You can go to this site, and if you want to become an ISP, you will need to peer through one of these things. It's not very expensive to connect in the interconnection point, but of course you will need peering agreement with Swisscom and Deutsche Telekom, and that might be more expensive. So, and this is how the internet is really organized today. So you have lots of operators, and then the game for the big operators is to connect to many interconnection points where they peer with hundreds of other operators. When you do that, you have a problem. Here I'm showing, for example, four domains that are connected, but they connect in the same interconnection point. So the rules of BGP says, come with your BGP router and connect to all the neighbors. Of course, you don't come with a BGP router, although you could, but you rent some computers or some routers in racks of this interconnection point. If you do that, you have an E-BGP mesh. You have inside this interconnection point, everybody wants to connect to everyone. So just like we wanted to avoid the I-BGP mesh by putting cluster and cluster heads, you can do the same thing, and then you obtain what is called a route server. So a route server is essentially a computer that acts as a BGP speaker for all the intermediate parties. So instead of having A here talk to B, like you should do normally, A will talk to this route server that will act as a mailbox and send the information back to this one. So if you're connected to 100 different peers or customers in this interconnection point, you don't need to have 100 TCP connections. You just connect to the route server here. Route servers are visible because very often the statistics and the information we have about BGP comes from route servers. So some route servers accept to publish some of the information they obtain so that we can see what are the BGP messages that help us discover what is the structure of the internet here. Last, as we can expect, we haven't spoken of security, which means the thing is insecure, and that's how it is today. Here's an example of attack that you can do. Here I'm showing again my example with 3 ISPs, and I have a customer here, which is EPFL. That's the prefix of EPFL for IPv4, a 15-bit prefix. That's passed, advertised by ISP2 to ISP3 and ISP1. Assume ISP3 is bogus, is malicious. Now, should ISPs be malicious? Well, in principle not, they are doing business. But some ISPs are under the control of their governments. In fact, many. We live in a democratic country here where we expect ISPs to be regulated, but play a fair game and do not manipulate things. But this is the minority of governments in the world. I mean, many governments don't have that kind of freedom that we have here. So they control their ISPs. So their ISPs, they control in particular the DNS, that we'll talk in a few hours, and BGP. So in some countries, you cannot access some sites in other countries because this country doesn't like it. Right? There was in history, there was a case where one country didn't like YouTube because they thought it's against their religious principles. So they did an attack against YouTube. And here is how the attack went. The malicious ISPs sends malicious, pretends that this prefix assume they want to attack EPFL. So you inject into ISP1 this advertisement. Here is the destination prefix, and here is the path here. Now assume somebody is here in C1 and wants to connect to us at EPFL. What will happen? Will this attack, shown here as it stands, be successful? And the majority says B, but many people say A. Well, in fact, it depends whether what will happen in terms of aggregation. If ISP1 performs aggregation, because now we have, ISP1 has probably received from ISP2 the advertisement, the legitimate advertisement. So there are two competing routes that are received by ISP1. Depends on the rules that ISP1 will do. If ISP1 accepts them because the routes are routes that are coming from peers, so ISP1 will certainly not advertise it to other peers, but it will advertise it to its customers. So it will advertise to C1. Now, if ISP1 does not aggregate, then we have three different routes. Remember, routes for overlapping prefix are considered separate routes. So ISP1 will have those three routes. If it accepts all of the routes, then anything that goes here will go to the most specific route, longest prefix match. Therefore, it will go this way. So the answer is the attack will succeed and all traffic will go here. If ISP1 is trying to aggregate, if it has a large network, for example, and it cares about having as few prefixes as possible, then it might aggregate these two into one, and then you have two competing things. If it uses hot potato routing, it's possible that some of the traffic, depending where C1 is, goes this way. So some fraction might go there. Voila, we'll do a break now and resume in 15 minutes.